Okay, welcome everyone to another live session for the online class, and ready to take your questions.
All right, the first question from our live viewer is, do you have any tips for viewing the close encounter with Mars that will take place next week?
I mean, Mars is one of the brighter night sky objects, and this is a pretty unusually close approach. That's not dramatically obvious, so you really need a small telescope to see Mars as other than a little red spot in the sky. So it's not dramatically brighter or closer than it is at any other time. Mars varies its distance from the Earth by about 30 or 40%. So this would only be properly seen through something like a 6 to 10 inch telescope. Binoculars really won't quite cut it, so you'll have to get together with an amateur astronomer or someone who has a small telescope on a reasonably dark side.
Let's see, the next question is, what is the size of the observable universe?
So the observable universe in the current cosmology, which is an expanding universe model with dark energy and dark matter, which is currently in an accelerating phase as dark energy dominates. It's a calculated number based on the expansion rate, history, and the components of normal matter, and dark energy. And that number is in any direction 42 billion light years. The standard reaction from people who know the age of the universe to that is surprise, because the universe is about 13.8 billion years old. So you would imagine the universe couldn't be more than 13.8 billion light years in any direction, even at light speed. How could it be essentially 3 times that distance in any direction to the observable edge? And the answer is because for much of its history, essentially for the first third of its history, the universe was expanding faster than light speed, which is to say, in the expanding space-time model described by general relativity, any 2 points in space-time were moving apart at faster than light speed. And it was only after deceleration by dark matter in that first phase of the universe's expansion that expansion rate dropped below the speed of light, and so more distant regions would come into view. So that's the size of the observable universe. So the diameter is twice that number, about 90 billion light years.
All right, the next question is from our live viewers who asks, what is the origin of the intense magnetic field of neutron stars?
So all stars are threaded by magnetic fields. The primordial gas and dust out of which stars form is threaded by mostly chaotic and very low level magnetic fields. And as that material collapses and in conserving angular momentum starts spinning and form a gravitationally bound object, the threaded magnetic field is trapped in the collapsing gas or plasma because it's hot enough that the electrons have been removed. And so if you essentially think of squeezing loosely distributed magnetic field lines, they get squeezed into a quite significant magnetic field of a normal star. So normal stars like the sun are threaded by a magnetic field, and that magnetic field sort of builds and then dissipates because the sun and other stars rotate differentially, which they're not solid objects. So they rotate faster around their equators and at their poles, and that sort of gradually winds up the magnetic field, and at some point it's so tightly wound that the magnetic field lines reconnect and it dissipates, and so the magnetic field builds up again, and that's the solar cycle. Now, when you have a star at the end of its life collapsing to a new configuration because there's no pressure support from nuclear reactions, a neutron star is a dead star. It's what's left over after the death of a massive star. Then again, in that collapsed phase, the magnetic field lines that were pre-existing are also trapped in the collapsing object, and so they're compressed to a much higher level and a much more intense magnetic field. And the amount of collapse, the factor by which the size reduces, pretty much gives you a hint as to what the magnetic field density is. So in neutron stars, I think the standard or typical magnetic fields are about 1 trillion Gauss, where a refrigerator magnet or something like that is probably 100 Gauss or something like that. So tens of billions of times stronger than a sort of terrestrial magnet or the Earth's magnetic field. There are even more extreme objects where the magnetic fields get up to 1,000 trillion Gauss, or 10 to the power 15. But all of this intensity of magnetic field comes from the collapse of an object to an extremely small size compared to a normal star.
All right, the next question is from Muzahir, who asks, if white dwarfs are dead stars and there is no nuclear fusion inside their core, how if there is no fusion to balance the gravity, do they not collapse in on themselves?
So the physical state of white dwarfs was first understood in the 1930s, about a century ago, and probably the most important person in that in those insights was Subrahmanyan Chandrasekhar, the Indian-born naturalized American astrophysicist, generally considered one of the greatest astrophysicists in the 20th century. He was a Nobel Prize winner, editor-in-chief of the Astrophysical Journal for decades, just a very extremely important and influential figure in astronomy. And he, over a period of a decade, worked on the physics of the interior of dead stars, collapsed stars. So what happens for a low-mass star, because the white dwarf is the endpoint of low-mass stars like the Sun, including the Sun, and up to about 1.5 to 2 times the mass of the Sun, all such stars will lose some of their mass in later phases of their life, like planetary nebula or red giant phase. So they expel some of their initial mass into space, and then the core collapses to a white dwarf that's most typically about half the mass of the Sun. With no fusion reactions creating energy to puff out the gas or sustain its size, the physical process that stops the star collapsing to nothing or to a point is called electron degeneracy pressure. And it's essentially a phenomenon in physics associated with the Pauli exclusion principle, which is a foundational idea in particle physics, where no two particles can have exactly the same quantum properties. Quantum properties being spin, electric charge, position, momentum, etc. And so this physical principle that's foundational to quantum theory applies to an entire star. And what that means is the star cannot collapse to nothing because there's this pressure force that results from particles not wanting to occupy not just the same space, but have exactly the same set of quantum properties. So Chandrasekhar calculated the degeneracy pressure, and that allowed him to understand the sort of equilibrium, the new equilibrium that a white dwarf reaches when it stops collapsing, where the balance is now between gravity pushing inward and this electron degeneracy pressure pushing outward. And of course, that is a much more collapsed state than a normal star. The density is billions of times higher than the central density of the Sun right now as a fusion burning star. And these are bizarre objects. They do have some energy. They radiate into space. Some white dwarfs are quite hot, from 10 to 20,000 Kelvin, and they can get ranged down to cooler white dwarfs. With no new energy source, basically they're just slowly radiating like a black body out into space, and they slowly cooling down. So white dwarfs have what's called a cooling curve. They will radiate their internal energy slowly into space and gradually dim and darken and turn into what you might call black dwarf.
All right, our next question is from Kushal, who's on with us live, who asks, what is gravido-electromagnetism?
It's just a catch-all technical term to talk about any physical situation where you actually have to invoke both the force of gravity and electromagnetic force. This is not the typical situation in physics or in astronomy, because the gravitational force is many orders of magnitude weaker than the electromagnetic force. So the only situations where you have to simultaneously consider gravity and the electromagnetic force are, of course, situations of intense gravity. And or the very early phases of the universe, like the Big Bang.
Right. The next question from a live viewer asks, can you explain how the IceCube neutrino detector was able to pinpoint the source location to the specific area in Orion?
Right. So let me back up and talk about the discovery just this last week or so. One of the really a major discovery of the year in astronomy. The IceCube, to this point, until a week or so ago, the only objects in the universe that have been detected in neutrinos were the sun, first detected decades ago, and supernova 1987A, a sort of relatively nearby supernova going off in an adjacent galaxy where something like 7 or 8 neutrinos were detected by a Japanese detector in 1987. So this was a truly important event when a neutrino detector in the Antarctic detected a single neutrino, not just from a nearby dying star or the sun, but from an active galaxy 4 billion light years away. So this is a pretty important event, and it's got a lot of news coverage. So neutrinos are abundant particles in the universe. There are as many neutrinos as there are protons, electrons, and neutrons. So they're super abundant, but they pass without notice because they do not operate, they do not obey the electromagnetic interactions, and so they have very weak interactions with matter. Typically, a neutrino could pass through, 10,000 miles of solid iron with a small likelihood of interacting. So they pass through normal matter as if it wasn't there. So if you want to make a detector of neutrinos, you're actually having to rely on the pretty rare encounter of a neutrino with a particle that transmits energy to it. And so the IceCube detector was built in the Antarctic to detect neutrinos using the pristine Arctic ice. It's extremely pure, and essentially they melt holes in the ice and drop arrays of detectors. And so interior to the ice in Antarctica, on a sort of kilometer cube of ice, there are thousands of detectors. Now, what are they actually detecting? The neutrino coming from a cosmic source, especially this source, an active galaxy, is extremely energetic, has a lot of energy. And so in the rare instance where it interacts with a normal particle, an atomic nucleus, it transmits energy to that atomic nucleus. And it's the mechanical energy transmitted to another nucleus by this tiny evanescent particle, a neutron, that is detected in the IceCube detector in the Antarctic. And so it's looking at the mechanical energy deposited by the neutrino that propagates through the array of detectors. And the directionality comes from the fact that you're detecting that energy through a volume. And so you can pinpoint the direction, and then you can point that direction backwards on the sky to identify, in this case, a region near Orion. Now, that alone would not allow you to identify it with an astronomical source because it's not pinpointing a tiny patch on the sky, just a sort of broad general direction of tens of degrees. The pinpointing to this active galaxy happened because essentially simultaneous with the release of this energy was a burst in this blazar. It's called a blazar, which is just a shorthand for one of the types of active galaxy. And so high energy emission was seen contemporaneously, given the travel time delay of 4 billion years, in this blazar that led to the neutrino being detected on the Earth. So this is a prototype of a brand new type of astronomy. It's called multi-messenger astronomy, where you start to be able to see astrophysical objects in multiple modes, either neutrinos or gravity waves or electromagnetic radiation, or hopefully all three.
All right, our next question comes from a live viewer who asks, in the Tools of Astronomy lecture about telescopes, you say that refractor telescopes have the problem of bending light into different focus points. What about apo telescope? What about apochromatic refractors?
So yes, so a simple refractor, which is just to say a large lens, will of course disperse light. I mean, because if you just take a small cross section of a spherical, to just take a lens, a biconvex lens, a small section of that is essentially like a prism. It's like Newton's prism. It will disperse light into colors. So yes, it is possible, and of course camera optics have used achromatic lenses for a long time. So camera optics need the different colors of red and blue, yellow, green light to come to focus at the same place. Otherwise, you wouldn't be able to make crisp images on all colors of the spectrum. So you can have achromatic optics, and that technology and those design principles have been known for decades. The trouble is when you scale achromatic optics up to large size, and by large size I mean bigger than something you put in a camera, something you put in a telescope, you have two problems. First, the optics become extremely large, and therefore they're hard to sustain without bending and sagging. So glass is not actually a true solid. It does flow very slightly and very slowly. And so making an achromatic refracting telescope ends up using a huge amount of glass. And so the second issue is to do these achromatic correctors often involves multiple elements. So it's not just a single extra piece of glass. Sometimes it's 5 or 6 cleverly designed with slightly different refractive index pieces of glass cemented together. So to do an achromatic refractor of the size of a meter, which is the Yerkes refractor, the largest that was ever seriously used for research, would involve an enormous amount of glass. So you're probably multiplying the mass of the refracting elements by a factor of 3, 4, or 5. And it's also going to get incredibly expensive. Machining these pieces of glass, doing it for camera optics is now really simple and can be mass produced. But when you have to do customized achromats, in some cases, taking it up to a foot in size, then the cost becomes tens or hundreds of thousands of dollars. So the expense and difficulty of doing that for a telescope of a meter across is just prohibitive.
Our next question is from a live viewer. Sarah asks, do you think we will be able to find preserved biosignatures on Mars?
That's a great question, and obviously people would love to know the answer to that. The best guess, of course, is that the surface of Mars has been sterile for quite a long time. Since Mars lost its atmosphere, it has been exposed to cosmic rays, damaging radiation, pulverizing impacts from micrometeorites. And so the Martian surface, by which I mean the top few centimeters of soil anywhere on the surface, is probably sterilized. It'd be very unlikely to find any kind of biosignature right on the surface or very near the surface. Underneath, though, is another matter entirely, and that's obviously where people are looking when they eventually get the technology to do so. We are almost certain there are subsurface aquifers on Mars. There's a lot of indirect evidence of that. And so if there are subsurface aquifers or water kept liquid by pressure and mild internal heating, then obviously you could have microbial life. It's possible. Or you just could have had that situation in the distant past, even if that current situation doesn't persist. Aquifers don't last forever. And so there may be places where we suspect there was an aquifer where you might find microbial fossilized forms of life. So both are in play for NASA's future missions, either trying to find existing present-day microbial life, that would be, of course, incredibly exciting, or only slightly less exciting, finding fossilized biosignatures. Now, biosignatures of microbial life are tricky. This is difficult work even to do on the Earth. When people look for the earliest forms of life on the Earth, which is to say 3.5 to about 3.8 billion years ago, the evidence is very indirect, which is to say these biomarkers are not actual fossils. They're not like body fossils, because you need macroscopic creatures, larger than the head of a pin, to actually leave something that's a recognizable fossil, even a very small one. The traces of life on Earth going back that far are essentially chemical or biochemical indirect signatures, imbalances in radioactive isotopes that are localized in a rock and indicate a metabolism was at work. So that's an indirect argument, and that's pretty much the argument that we'll probably have to use on Mars, because it would be very unlikely and amazingly lucky to find a body fossil or a macroscopic object that looked like even a tiny fossil on Mars. It's going to be the same kind of indirect biomarker evidence that we use on the Earth to look at the earliest forms of life on Earth. And people debate those forms of life on Earth. There's huge debate over the quality of the evidence that life existed on the Earth, say 3.8 to 3.7 billion years ago. Some researchers simply don't believe the evidence, and the evidence gets a lot better 3.5 billion years ago, and then by the time you get to 3 billion years ago, you have fossilized colonies of microbes, stromatolites, and at that point, nobody disagrees. So could we find stromatolites on Mars? Yes, it's possible. Absolutely. There may have been times and places where stromatolites or more complex creatures existed, but how do we locate those places when they're likely to be underground? And Mars is a big place, not as big as the Earth, but pretty big. That's a huge question. And NASA, of course, only has the money, and private space companies are not going to do this work. They're trying to do tourism and raise money. NASA only has the money to go 1 or 2 places on Mars to do these experiments. So how do you pick? How do you find the place to look? There's a lot of argument about that.
All right, our next question is from, excuse me, from Kushal, who's on with us live, who asks, can 2 protostars collide? And if so, what happens during that collision?
Protostars definitely can collide, and that probably happens quite a lot because our models of star formation and our view of stars forming in the nearby universe suggest that stars form in dense clusters. There are open clusters of stars, something like the Pleiades, where the star formation region is rather dispersed and there's not a high density of stars as they form. They're loosely aggregated by gravity, but there are definitely regions. This core of Orion would be a good example, the Orion molecular cloud, where stars form in very close proximity. And in that situation, it is indeed possible, and almost certainly it happens, that a protostar, or a star that's not yet fully collapsed or is about to be star but isn't yet, collide. What happens? It depends on the impact and the velocities. The velocities can be large enough that the 2 protostars may actually disrupt each other or rip each other apart by tidal forces. So it's quite possible that a protostar collision could lead to the destruction or the dissipation of both protostars, and you don't get any star resulting. And in any case, the velocity of collision, even if it's a glancing blow, is very high. And so these collisions are likely to be disruptive to the protostellar object. So in most cases, it will probably quench the star formation by dispersing the gas back out into space. It's very unlikely that the simplest possible imagined situation will occur where 2 protostars come together, merge, and form one new star of twice the mass or of the combined masses. That's actually the least likely outcome.
All right, our next question comes from a live viewer who asks, do you believe that we will be able to travel through a wormhole in the future, and will it take us to another galaxy or maybe another dimension?
So it depends on what you mean by the we. If you mean by the we, me and you, no, I don't think so. I don't think anything with wormholes is going to happen in our lifetimes, or even maybe in the somewhat longer future of centuries or millennia. Partly, so the issues here are, do wormholes exist? That is to say, are there places where space-time is pinched off or multiply connected, or in a complex topology that allows you to spontaneously go from one place in space-time to another place in space-time? That's, in shorthand, what a wormhole is. General relativity does not rule that out, and if you've read the popular book by Kip Thorne on gravity, wormholes, I think curved space-time and wormholes, I think wormholes even in the title of his book. It's a very good popular book. He as one of the preeminent gravity theorists alive, also does not rule out wormholes and says they're entirely possible within the theory. Now, the fact that something's possible within the laws of physics doesn't mean that it actually happens. And so that's simply out there as a possibility. We've seen no indication of a wormhole. We've definitely seen, obviously, collapsed objects, so the existence of black holes is pretty much beyond doubt. And a black hole is a region of space-time that's sort of pinched off and separated from the rest of the universe. But it does not itself imply that that region of space-time connects to another region of space-time. A wormhole is something quite different. It's a portal between two places in space-time. A black hole is just a sort of pinching off or the excision of a piece of space-time. So we've seen no sign that wormholes exist. It's also actually difficult to know how to look for them or what they would look like observationally. So while allowed theoretically, astronomers really don't have much idea of how to look for them. Also, space-time is mostly quite simple and flat. The universe is basically flat on large part, although at the beginning, at the Big Bang, it wasn't the case. So black holes are pretty unusual situations where space-time is that curved. So there's no indication from the large-scale structure of space-time in cosmology that the universe should have wormholes in it at all. That's not to say again that it isn't possible. It's just that our universe doesn't seem to be structured that way. And then the other thing is, presumably like black holes, or maybe even more scarce than black holes, wormholes are not going to be abundant in the universe. The nearest black holes are that we can confirm are hundreds of light years away, which is to say hundreds or thousands of trillions of miles away. So the practical issue of traveling to a wormhole is going to require us to be very comfortable traveling large distances through space, even if we could find one.
All right, our next question is a follow-up to an earlier comment, an earlier question, and it's in your earlier answer, you mentioned that for the early history of the universe, any two points were moving apart faster than light speed. But I think there's some confusion, but doesn't that depend on how far apart the points are? But there's actually two time periods, I think, that you were discussing. Right. So let's...
So the Big Bang model or theory, which is a theory that uses general relativity to describe gravity in space-time, essentially describes how any two, I mean, that's the key, any 2 points in space-time, they could be a meter apart or a kilometer or 100 or 1,000 or 1,000,000 light years apart. Any 2 points in space-time, how fast they're moving apart at any period after the Big Bang. The theory just gives us, from the expansion history of the universe, you can trace back from the current expansion and knowing what the universe is made of, you can calculate that number, that space-time expansion between any 2 points. It's an arbitrary thing. It doesn't depend on the scale you're looking at. It's scale-free. And so it's referencing that statement that you can say when the epoch was when before that, all points in space-time, wherever they are, if you measured their expansion rate, it would be faster than light speed. So it's a very general statement.
All right, our next question is from a live viewer who asks, which exoplanet is currently the best candidate for possibly supporting alien life?
That's actually now becoming a very hard question to answer. It was, for a while there were favorite exoplanets. The Alpha Centauri system has a possible Earth-like planet, and that's a hot favorite just because it's nearby. It's the nearest star system. I actually don't know which is the currently best Earth-like system. In numbers, there are probably of order 100 Earth-like planets, which is to say within a factor of 2 of Earth's size or mass, where the implied temperature on the surface would be within the range where water could be a liquid. The big caveat there is we don't know what the atmospheres of these planets are. We don't know what kind of an atmosphere Earth-like planets retain in other parts of the universe. It doesn't have to be like nitrogen and oxygen like ours at all. The oxygen, of course, here produced by life. And the temperature and an atmosphere obviously creates a greenhouse effect, or it creates just a thermal blanket, and so it significantly alters the surface temperature. So the whole habitability idea for exoplanets depends on information we don't have, which is to say the nature of the planet's atmosphere. It also depends on the eccentricity of the orbit or the inclination of the orbit. So the Earth has seasons caused by its axial tilt of 23.5 degrees, and the Earth is also in a mostly circular orbit, only deviating by a few percent from circular. Many exoplanets and most exoplanets have much larger ellipticities in their orbits, and that may make them less habitable because they'll have more extreme seasons just due to the difference in their closest and furthest approach from the star. So these uncertainties are enough to mean that the game of saying what's the most habitable exoplanet is really hard to do now. But they're probably, out of that 100, there are probably a dozen where all the conditions look pretty right for life. It's close to Earth-like as you could imagine.
All right, our next question from a live viewer is, Ryan asks, does electron degeneracy pressure apply to black holes?
No, so the electron degeneracy pressure is the physical force or principle that maintains a white dwarf at its particular high density. In the case of a black hole, the mass of the collapsed object is actually sufficient to overcome electron degeneracy pressure. And that's pretty much the transition that happens about 1.5 times when the core of the star, the dead core of the star, is more than about 1.5 times the mass of the sun. At that boundary, which was defined by Chandrasekhar about 100 years ago, gravity overcomes this quantum mechanical force, electron degeneracy pressure. And then you have a neutron star. And then you, of course, crush down to pure nuclear matter. So a neutron star is essentially like a giant atomic nucleus, where in a reverse version of beta decay, electrons and protons combine with the emission of an antineutrino to form neutrons, and you have pure neutron material with no electrical force. The nucleons can just sit right next to each other, so it's like a pure atomic nucleus. And at that point, it's held up by neutron degeneracy pressure, a different quantum force. If you go beyond 3 times the mass of the sun for the stellar remnant, then the gravity will even overcome the neutron degeneracy pressure, and then you have a black hole. So these are the transitions or the demarcations for collapsed stellar objects, where there are nuclear forces, quantum forces that sustain a particular size, but beyond a certain mass, they are overcome and you collapse. You end up with an event horizon and, by implication, a singularity at the center.
All right, our next question is, what doors will neutrinos open to us in exploring the universe?
That's a very important phenomena to be able to detect neutrinos. So the IceCube detector is now, successful, we think, and should continue to do astronomy and detect new astronomical sources. There were other experiments. There have been other neutrino detectors. There was actually a project that was being tested when I was a postdoc in Hawaii 30 years ago called DUMAD. It was the attempt to put neutrino detectors in the deep ocean trench, the Maui Trench, I think, between Oahu and Maui. So it's a similar idea. It just is arrays of detectors turning into a grid or a cube looking for neutrino interactions with the water molecules. It just turned out that is a less robust way to do it. The ocean is just too changeable. There's marine creatures, there's contaminants, there's pollution, there's changing currents, etc. So DUMAD was an interesting prototype, but it was realized after a while that using frozen water, i.e. the Antarctic ice, was a much better way to go because it was stable, incredibly pure. Once you got some infrastructure near the South Pole and the Antarctic to build a base camp, it's not too expensive to build the array. So now we have the IceCube array, and it's an amazing detection of a very distant active galaxy. It should be anticipated that it's going to detect other cosmic sources. So now we know that supermassive black holes, the object that was detected was called a blazar, and it's essentially an active galaxy where there's a supermassive black hole, probably 1 billion or so times the mass of the sun, accelerating jets, and in those jets, particles are accelerated to super relativistic speeds and extremely high energies, and then eventually they come to the Earth. So we can anticipate more neutrinos being detected that originated in the environment of a supermassive black hole somewhere in the distant universe. So that's probably the biggest game that's going to be played with these new detectors. It is also possible that neutrinos from the Big Bang could be detected. That's a much harder experiment because it's harder to, first of all, the neutrinos have a much lower temperature or energy, and also their time signature is not clear. There's an ambient background of neutrino radiation in the universe, just like there's an ambient background of electromagnetic radiation in the universe, it's not exactly clear how you would design a detector to see the Big Bang in neutrinos, and IceCube is probably not going to be able to do that.
All right, here's a big philosophical question. Does time even exist, and can we understand time?
Possibly not. That's a good question, of course. Space and time are concepts that are pretty abstract. They have meaning in physics only up to a point. Space is perhaps easier to understand than time. And, you know, if you've read Stephen Hawking's famous book that's now been reproduced endlessly, it's 30 or so years old, A Brief History of Time, he actually gets into quite a lot of detail about the nature of time. It's not a philosophical book, it's a physics and cosmology book, but he addresses the issue of the origin of time. How does time emerge in a universe that originally was timeless? Because at the point of the Big Bang, there is no time arrow, there is no time to measure. You can define that as an event and say how long ago it occurred, but time itself becomes meaningless in the Big Bang. And Hawking addressed that issue, and other cosmologists have. So with that as a background, it's obvious that there are situations that we would like to understand physically where time does not mean the kind of thing that it does mean to us now. You know, we measure time with oscillations of atoms, with astronomical orbits, or the spin rate and decline of neutron stars or pulsars. These are our cosmic clocks, or our atomic and molecular clocks. And there was a point in the universe going back when those clocks didn't exist. So how would you actually even mark time except as a pure theoretical concept? So that's a very big practical issue. There are certainly situations in the universe where time has no simple way of measurement or even definition in the way we talk about measuring time. And then, of course, in physics, there's a whole different issue. At the level of microscopic physics, there is general reversibility of time in all subatomic reactions, with an important caveat. In the triple conjugate of fundamental properties of subatomic systems, there's the arrow of time, the time axis of an interaction, which could flow forward or backward in time. Both are seen in different situations. There's electric charge, which could be positive or negative, and you can imagine a subatomic reaction where you change the charge on all the particles, and that's a plausible interaction too. And then there's parity, which is essentially a spin idea. So a spin operator could be pointed up or pointed down, and you can flip those. So in the general symmetry of physics to those three operators or relationships, it's not a complete symmetry. So there's an indication that some of the asymmetry or the arrow of time may come from the fact that that triple symmetry is broken somehow in ways we don't fully understand. So I would say at the level of just fundamental physics, time still has mysteries. The asymmetry of time, the arrow of time, where does that come from? And then at the level of operational measurements in some situations in the universe, we're also struggling to understand time.
All right, Kushal, who is on with the slide, asks, is Oumuamua a comet or an asteroid?
They're calling it more an asteroid at this point. So, I mean, the distinction between comets and asteroids in some cases is slightly moot. Comets are, I mean, there's the spatial distinction between comets and asteroids as opposed to the compositional difference. Comets are presumed to inhabit the Oort cloud, which is a extremely large, extending to thousands and tens of thousands of astronomical units, a spherical cloud around the solar system, a sort of primordial relic of the early collapse of the solar system. And these comets, these objects, are in highly elliptical orbits, meaning they spend the vast majority of their time at very large distances, and some of them will loop into the interior, into the inner solar system. But many actually will never come within the realm of the planets. So those are comets, and they're of sizes of a few kilometers typically, and they will have frozen gases or ices in them and rocks, a mixture of that. The ones that periodically journey into the inner solar system near the sun will gradually get their ices and volatile materials baked out and turn into pure rocks. Asteroids classically live in the asteroid belt. They're rocky debris left over, essentially a failed planet. The sum of all the asteroids in the asteroid belt, main belt, is about 4% of the mass of the Earth. So even though there are many of them and they range up to hundreds of kilometers in size, they don't amount to a hill of beans if you add them all together. A very small planet. And some of those also get deflected by collisions or just gravity interactions out of the asteroid belt into Earth-crossing orbits or looping through the solar system. So for an individual object, you could have an ambiguity between whether it's a comet or an asteroid, because if it's traveling through the inner solar system, you'd need to know its orbit pretty well to be able to distinguish between it. But the object you're asking about is generally considered an asteroid.
All right, our next question from our live viewers has to do with black hole mergers. I imagine that lots of black hole mergers have taken place in the history of the universe. How come LIGO isn't detecting lots of gravity waves from these mini mergers?
That's right. I think I just finished a book on black holes, and I remember a number I locked in on, which is that somewhere in the universe, a pair of black holes are merging pretty much every second. So yeah, it's happening a lot. But of course, the universe is a huge place. That's the key. And so the black hole mergers are producing incredibly subtle and small signals, ripples in space-time. And LIGO just had the sensitivity to detect these. So now the black hole mergers that LIGO detected, they were not that nearby. Gravity waves diminish with distance from the source by just the inverse of the amplitude, as opposed to light and gravity, which diminishes the inverse square of the distance. So LIGO has a decent grasp of gravity waves out in distance, but just the size of the signal is so small. The sort of space-time distortion of a typical gravity wave from a black hole merger is 1 part in 10 to the 21 of space-time. It's incredibly small. So that's the basic reason why LIGO is only going to detect occasional events. It's truly limited by sensitivity. The best guess is that when LIGO, further refines its detectors and lowers noise as much as it can, the basic infrastructure of LIGO is finished. There's nothing new to do with the array. There's just improvements to make with the optics and the electronics. It should detect, or could detect, about 1 event per week. So people have modeled this, and they think that in its full operation at its optimal efficiency, LIGO will be giving us dozens of gravity wave events per year. That's going to be pretty exciting, given that we've only had a handful so far.
Right, another one of our viewers has several questions about Roche limits. So maybe you could explain what a Roche limit is, and then the questions are, why don't we disintegrate within the Earth's Roche limit, or why don't spacecraft like Cassini disintegrate even after entering the Roche limit of Saturn?
So the Roche limit is named after a French astronomer from, I think, the mid-18th century, but don't quote me on that. It's a simple calculation in gravity, which is to say, if you imagine 2 objects, one massive one and one much less massive one, the force of gravity declines with the inverse square of the distance. So if you have an object of significant size in orbit of a much more massive object, the gravity on its its face or side that's nearest the large object is slightly stronger than the gravity on its far side, and that implies a stretching force. And so, that's a basic effect of gravity. Gravity is a differential force, an inverse square force. That, of course, leads to the tides on the Earth. The fact that the Earth is stretched by the sun, and the moon is stretched by the Earth because the moon is in close orbit of the Earth. So these stretching forces are just part of a standard gravity calculation. The Roche limit corresponds to the distance of a small object to a larger object in a gravitational situation, where that stretching force between the near and the far side of that object exceeds the tensile strength or the sort of internal integrity of the rocky material it's made of. And so at that point, the gravity is essentially pulling apart the object. It's just disrupting it, disrupting the material that it's made of, typically rocks. And so that's the practical definition of a Roche limit. And so you can do that calculation for any two objects, and you could decide how close the moon would have to be to the Earth, or how close the Earth would have to be to the sun for it to be ripped apart by the sun's gravity or the moon by the Earth's gravity, and that would be the Roche limit. So you can calculate this for any set of objects, for the moons of Jupiter, relative to Jupiter, and so on. And that's what the Roche limit is. And something inside the Roche limit will indeed be destroyed and disrupted, and we are fairly certain in the history of the solar system that objects have had that situation, and so have been destroyed by gravity, by the forces, internal forces of gravity, as they enter the Roche limit. It's hard to identify an object in the current solar system that's at the Roche limit or near it. Most of the objects we know about are comfortably away from the Roche limit, so they're not on the edge of being destroyed.
Right, the next question is, how did scientists predict the shape of the Milky Way as a spiral, and how did we find out how many arms it has?
I'm not sure that scientists actually predicted the shape of the Milky Way, but before they really knew the shape of the Milky Way, because we're buried in it, we're embedded in it, so it's a little hard to see its geometry, they'd speculated that it might have this shape. So that the spiral nebulae, which have been known since Herschel's time, so they've been cataloged, Immanuel Kant around the time of Herschel, so late 18th century, speculated that these spiral nebulae, as they were called, cataloged by Herschel and others, might be island universes, and they, by analogy, argued that the Milky Way, the system we're in, might be such an object. So their speculation was made a couple hundred years ago, actually. And we saw these examples. It's easy to see M31, M51, the nearby galaxies, with the telescopes that have been around for a couple hundred years, to see what a spiral galaxy looks of different orientations, to see that edge on, it's a very thin disk, but it's surrounded by a diffuse halo of mostly older stars called the halo, the galactic halo, and that has an interior sort of two fried eggs back to back, or peanut component of reddish older stars. Those are the three components of a spiral galaxy. And by the sort of early 20th century, astronomers had started to discern those components in the Milky Way, even though we're embedded in it, which does limit our ability to view that. And the key innovation, the bulge is actually visible fairly easily, so, but not with visible light because of the dust. So you look at the raggedy Milky Way in visible light or with an optical telescope, and you really don't clearly see the geometry of the Milky Way. So the bulge component of the Milky Way wasn't really clearly seen until we had infrared sky surveys, and that would have been the IRS satellite in the 1970s. So we didn't see the bulge component of the Milky Way until the 1970s. People had detected the diffuse halo, those faint, older halo stars with low fractions of heavy elements, early on with big telescopes, so the 1920s and 30s. And the 1930s and 40s were when we really saw the spiral structure of the Milky Way, even though we're sitting there buried in the middle of the plane because of radio techniques. So the radio telescopes, optical telescopes, cannot see through dust. To look to the center of the Milky Way galaxy with an optical telescope is like looking through a closed door. 1 in a trillion photons gets to us from the very center of our galaxy. But radio telescopes see easily through the gas and dust that's in the disk of the Milky Way, and by mapping the velocity of the gas clouds in lines of neutral hydrogen, typically, because most of the gas is hydrogen, they were able to map the velocity looking in all the directions from the Earth through the disk of the Milky Way and make a velocity map of the galaxy. They could see where the higher concentrations of gas were, so they could mark out the nearest spiral arms and then the more distant spiral arms. And this work took probably 15 or 20 years because the radio telescopes were improving through this time. But by the middle of the 20th century, radio astronomers had given us a pretty clear idea of what the Milky Way looked like, had mapped out the spiral arms, and had made it clear that we lived in a spiral galaxy.
Right. Kind of related to that is another question who you sort of answered that already, but we can address it directly, which is, can we see the stars that are exactly opposite us on the other side of the galaxy? Is there any way to see those?
Now there is. So the part of the Milky Way that's on the far side of the galactic center from us, and a sort of a range of angles around that direction. That direction, of course, is Sagittarius, because Sagittarius A star is the astronomer's name for the very center of our galaxy. It's an extremely compact radio source. It's the marker of a 4 million solar mass black hole whose mass has been measured very beautifully by stellar orbits in the last few decades. So that direction and a span of 10 or 15 degrees on either side of it and above and below it has been historically called the zone of avoidance. Zone of avoidance meaning optical telescopes essentially can't see through that gas and dust, and it's kind of useless looking there because all you see is stuff that's fairly near the sun, like a few hundred light years away. So for optical astronomers, it's the zone of avoidance. There's nothing you can see there. You can't count galaxies there. And it took infrared techniques for us to be able to do better than that. So with near-infrared imaging, that is wavelengths of a few microns, or say 4 to 8 times typical visual light, you can start to see through the gas and dust fairly well. So that those wavelengths let us see the bulge of our galaxy, and they started to let us see the far side of the galaxy. And so infrared surveys of galaxies that became a big deal in the 1980s and 90s, they actually were able to work in the zone of avoidance, because it's kind of a problem in cosmology. If there's this big chunk of the sky where you can't count galaxies on the far side of the Milky Way because you just can't see through the Milky Way, and that obstacle was overcome in the 1980s and 90s with infrared surveys. So the zone of we don't have to worry about the zone of avoidance anymore, because long wavelength surveys have let us see to the other side of the galaxy, count galaxies in those directions, see the far edges of the Milky Way across the galactic center from us, and so on.
All right, we have time for just a couple more questions. The first one I think should be relatively simple. Are there any neutrino detectors in space?
No. Just for a practical reason that neutrinos interact so weakly with normal matter, that the mass, both the mass and the volume of a neutrino detector are large. When I was an undergraduate, just heading off to grad school, and I thought I might do high energy physics, I actually worked on a neutrino calorimeter, sort of an experiment at CERN, the nuclear physics place in Geneva. I worked on an experiment to try and detect neutrinos by their interactions in metal with scintillators and photomultiplier tubes and so on. And this detector, this early CERN detector from the 70s and 80s, was essentially 3,000 or 4,000 tons of metal surrounded by detectors. So the mass of neutrino detectors is so large that it's prohibitively expensive to put these things in space, unfortunately.
And our final question for today is, can you talk briefly about how Lyman alpha blobs and galaxy formation go together?
Sure. This is something related to research I've done in the past. Lyman alpha, well, first of all, Lyman alpha is a strong emission line of hydrogen gas occurring at a rest wavelength of 1216 angstroms, sort of 0.1 micron. So it's in the rest ultraviolet. And typically this wavelength of radiation could only be seen with ultraviolet telescope, and the Hubble Space Telescope was really the first observatory that let us look at Lyman alpha properly. Now, if you look into the distant universe, then the redshift helps you out, because if you look at a redshift of 3, it's 1 plus z times the wavelength, so that's 4 times 1216 angstroms. That puts a Lyman alpha line or emission into the middle part of the green part of the visible spectrum. So you don't have to use the Hubble Space Telescope or ultraviolet telescope in space if you look at Lyman alpha in the distant universe. And of course, a lot of people are doing that, because these hydrogen emitting blobs of gas have been seen at very high redshifts of 5, 6, 7, even 8. And they're thought to be precursors of normal galaxies. So galaxies obviously not obviously, but in the model and in observations, they seem to have come together by clustering. Smaller galaxies formed first, they clustered into larger galaxies, and before things were galaxies, they were just diffuse blobs of gas, sort of eventually forming stars. So the lymanalpha blobs that astronomers like to observe, especially in the high redshift universe, are the very early building blocks of galaxy formation. So it's obviously very important to be able to map them out, see their physical state, because it's essentially telling us 10 to 12 billion years ago how galaxies first formed. So it's very active research, and it's hard. These blobs are faint, they're diffuse, they don't emit a lot of hydrogen emission in this line, and so you need 6, 8, 10-meter telescopes to do this kind of work. Thanks very much. Good set of varied questions as always, and we'll be back with you in a couple of weeks.
Thank you for Grant.
And thanks to Grant and Matthew for facilitating today.